1 and 2 conferences, you will see that many of the conclusions are drawn from simulations. But from the beginning, we have been doing those simulations following the Monte Carlo method. I will explain you what this exactly is later. But last year, Kees Bassa, Olivier Hainaut, and myself published an article. I will refer to this article in the slides as BHG22, but in my speech, I will say simply the article, all right? So in the article, we showed that satellite density follows an analytical probability density function. So this opens new doors to performing simulations in a very different way. So I will explain how to do this and which are the advantages and drawbacks of each of the methods, the analytical one and the Monte Carlo. Well, if you are interested in this, you may pay a look to the appendices to SATCON 1 technical report. There we set the basis for the first simulations we did to assess the impact of satellite constellations in astronomy. At the beginning, we started simply counting how many satellites are above the horizon or above a certain elevation. But later, we went deeper and we were able to simulate how many satellites are crossing the field of view at a specific pointing, at a specific elevation and azimuth, and with a specific definition of the satellite constellation, of course. Well, all those simulations were done following the path of each individual satellite in its orbit. This is much simpler than computing through orbits. So we have to forget about atmospheric drag, non-Keplerian potentials. So in our simulations, all orbits are circular, and satellites move at a constant speed. So this is simple, but the main problem is that you have to follow tens of thousands of satellites at every step of 1 second, 1/10 of a second, whatever. The advantages are that this is very simple from the conceptual point of view. The dynamics are very, very simplified, and the geometry is not too much complicated. Also, if you apply some kind of a smart prospection to the sample, you are not obliged to follow absolutely all the satellites in your sample. But if you are smart, you can reduce the number of satellites you follow, you can reduce it to the subset of the satellites that have some chance of crossing your field of view during the integration time. But in any case, even with this kind of smart prospection, you at the end are left with many satellites to follow. Also, this is a discrete simulation. So as you can see in this graph, if you perform only one shot, only one simulation of your integration, you get a lot of random noise. You have to average at least, in this case, 50 iterations to clean out that random noise. So you have to compute a lot to do this. Also, the lesser the number of satellites in the field of view, the more iterations you need to avoid a small number statistics. The extreme case is when you have no satellite in your field of view. You have to wait for a very long time to be sure that 0 is a good approximation to the number of satellites you have. And of course, computer time increases significantly with integration time. So that was the Monte Carlo or the discrete approach. What's the analytic approach? Well, you know that the shell of a satellite constellation is defined by its radius, the inclination, and the number of satellites. Essentially, that's everything we need to simulate the satellites there. We showed in the article that one single satellite in a circular orbit induces a probability density function that follows this simple function. We can see the function displayed here. This is for a satellite in an orbit with inclination 50 degrees, and you see that the function is minimum at the equator, and it increases as the absolute value of the latitude increases too. In fact, the density is diverging at the values of latitude equal to the inclination of the shell. So you get infinite density at some parallels. This can be seen not for only one shell, but for several of them in this graph by Kees Bassa, where you see how the different shells are overlapped, and you see the increase in density at the upper boundary of each one of the shells. By the way, we are not using this fact, not yet, in our propaganda, but we have reasons to defend that this statement is true. So don't worry, I will not include this image in the proceedings. But It is true. So Starlink is causing infinite density of satellites at certain regions of the sky. Well, this is technically true, but we should not say this in public because this statement is biased. Even Sputnik 1 was causing an infinite density of satellites at certain parts of the sky. No? Because we are not counting satellites by their density, but by their numbers. This means that what we have to do is to integrate the function, the density function. And even though the density is infinite at several points, the integral is not. So the number of satellites is never infinite. If you make the integral on some region of the sky or of the shell, we get the fraction of the sample that is contained inside the field of view. And in the article, we were admitting that the density is constant inside the field of view. So we got the density from the function, and we admitted that it was constant all over the field of view. So we simply multiplied the density by the field of view. But this is not strictly true, and this is the new contribution of this talk. The density function is not uniform in general. It is never uniform when you are very close to the shell limits, or when the shell limit is inside your field of view, something that may happen. And also, you have to pay attention to wide fields of view in general. For wide fields of view, the density function is never uniform. So the general solution should rely not on the mean value in the field of view, but on the integral over the field of view. Numerically, the integral is also easy. If you look to the article, there you can see that the integral is this, integrating between two parallels and two meridians. But we see that we can integrate only pieces of this shape, and our field of view is never that shape. Even square fields of view are never projected onto spaces limited by parallels and meridians on the shell. So we have to make some approximation, dividing the area in stripes limited by parallels and meridians, and integrate inside each of them. How to do integration? Let's see. These are the steps. In this graph, you have to define the observatory latitude, of course, the shell properties, radius, number of inclination, and number of satellites, the field of view, and the pointing direction. Then you have to find the intersection of your view cone with the shell. This is, in principle, a non-trivial geometrical problem. In this case, I am showing this intersection for an example. It is defined by 500 points in the view cone, and you see that the shape is, in general, is not an ellipse. It is a different shape. It's a complicated shape. You have the area defined by the conic bundle of lines intersecting the shell. It is the graph you have here. And after that, you have to divide the area into integrable vertical stripes. This would be an example. In this case, and you have to divide into a certain number of stripes, and you have to iterate, adding stripes, until you get the precision you want. So you need an iterative process here. This way, you get the instantaneous number of satellites present in the field of view at the beginning of the integration. But new satellites will enter the field of view during the integration. So from this number, n, you have to compute how many satellites will enter the field of view during the integration, taking into account the apparent angular speed of the satellites that you have to compute, and you can do that from the input data, integration time, and to dividing by the area of the field of view, not of the shape on the shell, but of your field of view. So you can compute everything. From the integration, you get the instantaneous number of satellites, and from this computation, you get how many of them will enter the field of view during the integration time. So that is not as simple as just integrating the function. You have to do a few more things. But you can find a few more problems during the way. Pay attention to the areas including the pole, any of the two poles. You will need a different approach to integrate the function in that cases. Be aware of the areas including the shell limit. This is easy to take into account. But you have also to take into account which areas are in shadow, totally or partially. When your area is in shadow, you have no satellites. When your area is in light, you have the previous case, as here. But when you have the shadow crossing your field of view, you have to deal with the problem in a different way. You have to find some way of deciding which parts of the area are in shadow, and you have to be sure that the integral there is 0. In this case, my algorithm sets the initial and final latitude for integration to the same value, so the result is 0 for those areas. In the light area, you can proceed normally, but you have to be aware that in the transition zone, several stripes have to be divided into 2 of them. So you have to handle this problem also inside your algorithm. And none of those checks is straightforward from the geometrical point of view, in fact. Well, we see that the computational weight of the Monte Carlo approach is transformed here into a more complex algorithm. We have several geometrical non-trivial problems. We have a couple, at least, of iterative processes. And at the end, the code is larger. In my case, my analytic code is 25% larger than my Monte Carlo code, but it is computationally much cheaper. I will show you some example. Here you have only one shell, a constellation made up from only one shell at inclination 50 degrees. And the field of view is 15 degrees, so it is a wide field of view. We are looking at the meridian from an equatorial observatory, from the horizon to the zenith, and back to the horizon, the other way around. So we are looking from the north to the south, counting how many satellites we have. The dots are a Monte Carlo realization of this problem. And the red line represents the analytic result. You see that, in general, all the dots are below the envelope of the analytic result. Imagine that you want to fill a circle with a random cloud of points. The diameter of the cloud will be always smaller than the diameter of the circle. And to get the diameter of the cloud of dots closer to the diameter of the circle, you have to perform a lot of random shots. This is the same. When you perform even more than 50 random shots, the dots get closer and closer to the analytic curve. And this effect is increased close to the shell boundaries, here and there, due to the shape of the shell boundary in the field of view and how satellites are passing and crossing. So as you increase the number of random shots, the Monte Carlo results approach the limit of the analytic results. But the main result is not this, that things more or less are similar. So if everything is the same, what's the gain in doing the things differently? The gain is in computer time. We have 10 seconds for all the analytical simulation and 40 minutes for the Monte Carlo one. Well, I know that my code is probably not the most efficient, but in any case, the contrast is huge.
2 minutes.
All right. This is the same constellation, but seen from an observatory at 45 degrees latitude. And you see that the behavior is slightly different, but you can get this result for all the pointing directions in a matter of seconds. And this is a more realistic simulation for the Starlink Phase 2 constellation. Here you see that one shell, it is not true. Here we have the Starlink 2 constellation with 8 shells, all right? And from an observatory at 45 degrees latitude. And here you see, as you go from the horizon at the north to the zenith, you see how the field of view is crossing all the shell boundaries, and you see those bumps in the number of satellites you have. So the problem we have is highly non-uniform. It was very evident from the Monte Carlo simulations we did years ago, but it is even most clear when we do this with the analytic approach. This is my last slide. In summary, so the analytical function from the article allows a radical change in philosophy. Many things have to be reversed, and the point of view is very different from the point of view of programming. The computational weight is transferred to the geometrical complexity, but you only have to solve the geometrical complexity once in your life. Hopefully. This approach is not really fully analytic. The function is analytic, but there are 2 or more iterative processes and some approximations in the way. I have shown that. And once you have programmed the savings in computer time are worth the effort. I think so. I will perform some more simulations to include in the proceedings stronger statistics about computer time that we can save with this kind of new approach to the simulation. So if any of you are doing simulations of the number of satellites in the fields of view, we invite you to change your mind and to follow the analytic way. That's all.
Thank you very much. We have time for probably one question. There's one online. Okay. Gotta find it. Yeah.
This is working. So Brad Young in Slack asks, how is the dynamic change in the number of lit satellites due to the change in shape of shadow at different elevations? The shadow is a conic section accounted for. And is any attempt to consider partial illumination in the Earth's penumbra?
Well, I am not sure if I understood the first part of the question. No, but the geometry solves everything in the sense that you have your field of view. In my simulations, it is circular, but the algorithm may accept fields of view with arbitrary shape, in fact, square or whatever. And you are intersecting your view cone with the shell, and all the computations are done on the shell. The integration is performed on the shell. So there is no geometric deformation of the function. You are directly integrating the original function. Your only problem is in which area you have to perform the integration. But I think that the question was this. And I have not included the penumbra effect, but it could be done. It would complicate further the geometry of the problem. You should add one more module to deal not only with the lit and the shadow area, but also with the penumbra, but it could be done. I have not done, but it could be done. But for these kind of simulations, I don't see clearly the gain of introducing this, in fact. But it could be done. Also, I did not show, but for each point on the shell, you can deterministically compute the apparent angular speed of the satellites, the position angle of their movement, and also the magnitude, if you have the right function to derive the magnitude, of course. But for each position on the shell, all those values are determined, deterministically determined.
Thank you.
You're welcome.